Good morning, dear student. In previous lecture, we already discussed the first evidence for the ligand substitution reaction. Okay, so in today's lecture, we are very much interested in the second evidence, that is for ligand substitution reaction, which is occur mostly through dissociative type of mechanism, that is your conjugate base mechanism. Okay, it is also known as SN1CB mechanism, that is substitution nucleophilic unimolecular conjugate base mechanism. So, how this evidence tell us that the reaction undergo dissociative type of mechanism. So let us discuss the base hydrolysis reaction of the cobalt third complex. So before discussing this conjugate base mechanism, so you should remember that is whenever the reaction, that is uh, if you consider CO NH35 X, it is in plus 2. This is the cobalt complex. When this cobalt complex, when it interact with water molecule, so we are very much familiar with this reaction, that is the X ligand, it is replaced by the water molecule, and this reaction, it is considered as a equation reaction. So are you all are familiar with this reaction, that is the replacement of the ligand from this reactant by water molecule. It is called equation reaction. So whenever we consider this equation reaction, it is also known as acid hydrolysis reaction. So you should keep in mind that whatever the equation reaction, that is the replacement of one of the ligand from the metal complexes by water molecule, it is called equation reaction, and this equation reaction, it is also considered as acid hydrolysis. When the same complex, when it react with the hydroxyl ion, that is OH minus ion, then it is considered as a base hydrolysis reaction. So at least you should know what is the difference between acid hydrolysis and base hydrolysis. So whatever we discuss, the second evidence, that is conjugate base mechanism, it is your base hydrolysis reaction. Okay, substitution nucleophilic unimolecular conjugate base mechanism, it is your base hydrolysis reaction. Okay, so how this reaction is going on, and what is the product, and either they undergo dissociative or associative type of mechanism, let us we discuss it. Okay, so at least you should know, whenever the reaction, that is equation reaction, it is also called as acid hydrolysis, and the second, that is whenever you used base such as hydroxyl ion, then it is considered as a base hydrolysis, that is one of the ligand, it is replaced by the hydroxyl ion or other than water molecule, then it is considered as a base hydrolysis reaction. Okay, then it is considered as a base hydrolysis reaction. So let us consider what is this reaction. So we are considering the cobalt complex as an example for this conjugate base mechanism. So we know that what is conjugate base. So whenever there is an acid, it will forms its conjugate base. That is, for example, this ammonia. In this ammonia loss 1H plus, it will forms NH2 minus. Okay, if you consider this ammonia, okay, this is an acid. Okay, for example, we are considering it is an acid. Okay, okay, the complex is acid, and then when it loss H plus ion, it will forms its conjugate base. And when this ammonia, okay, it will take H plus ion. Okay, so we can write, if you consider this ammonia, as a ligand, then this ammonia, when lost H plus ion, it will forms conjugate base, and when it will take H plus ion, then it will form conjugate acid. Conjugate acid. So this is your conjugate base mechanism. So at least you should know that this reaction, that is SN1CB mechanism, it is your base. Okay, conjugate base mechanism, that is your base hydrolysis reaction, means you have to use base such as hydroxyl ion, and this hydroxyl ion, it will abstract one of the proton from this ammonia ligand. Okay, and there is a formation of conjugate base. Okay, formation of conjugate base, and therefore this mechanism, it is considered as a conjugate base mechanism. So let us discuss the reaction first, and then we will discuss the mechanisms and the important points regarding to this reaction. That is this is the reaction, that is cobalt NH35. This is your X, or we can consider this is your Cl, it is in plus. Okay, so this cobalt, it is in +3 oxidation state, so you should keep in mind. Okay, cobalt, it is in +3 oxidation state. The first reaction with the reaction of this cobalt third complex, cobalt ammonium complex with hydroxyl ion, and the first step is your equilibrium step. The first step is your equilibrium steps, and we get here CO NH3 4 times NH2. Okay, so this is the reaction. So this base, okay, when this hydroxyl ion, it is act as a base, then this metal complex, it is act as an acid, so it is a proton donor. Okay, so one of the ammonia ligand, it will donate its proton. Okay, and it will forms its conjugate base. It will forms conjugate base such as NH2 minus. So CO NH3 4 times NH2, and then there is a X, and due to this conjugate base formation, the charge on this complex is decreases by 1 unit. The charge is decreases by 1 unit, and we get one water molecule, and this is your equilibrium reaction. This is your equilibrium reaction. This is your equilibrium reaction. If you consider this reaction, so this is the first step, that is the cobalt third complex, cobalt ammonium complex, react with hydroxyl ion. So whenever hydroxyl ion, it is considered as a base, then this complex, cobalt ammonium complex, act as a prostate acid. So it will donate its proton, and it will forms its conjugate base such as NH2 minus, and due to this, the overall charge on the complex is decreases by 1 unit. This is an equilibrium reaction. If you consider the rate, it is directly proportional to the concentration of reactant as well as concentration of hydroxyl ion. And what it indicate, the rate, which is equal to K2 into concentration of reactant into concentration of OH minus ion, and this indicate the reaction is second order. Okay, the reaction is second order, and it undergo associative type of mechanism. It will shows associative type of mechanism. So if you consider the kinetics of this reaction, according to this kinetics, the rate is directly proportional to the concentration of reactant as well as concentration of hydroxyl ion, and the overall reaction is second order reaction, and it will follows associative pathway for the ligand substitution. But if you consider that when it undergo associative type of mechanism, whatever the intermediate or the activated complex must be of higher coordination number is formed, that is coordination number 7, with geometry pentagonal, bipyramidal, or cap octahedron is formed. But the experimental study indicates that such a kind of intermediate or activated complex with higher coordination number is not formed in this reaction, is not formed in this reaction, and therefore this reaction it is considered as a SN1. Okay, this reaction is considered as a first order reaction, means the rate of the reaction it is not depend upon the concentration of this hydroxyl ion. So kinetically it is second order, and it is we know that when it is second order then it follow associative type of mechanism, but experimentally it is studied that the intermediate or the activated complex with higher coordination number is not formed in this reaction, and therefore this reaction is your uh, first order reaction, where the rate of the reaction is totally depend on the concentration of reactant only, and therefore it is considered as SN1. So it undergo dissociative type of mechanism. It will shows dissociative type of mechanism for ligand substitution. Okay, and the conjugate base is formed, therefore it is considered as a SN1 conjugate base mechanism. So let us discuss the second step. So this is an equilibrium step. According to this it is second order, but it is not true. Practically the intermediate is not identified, or we can't get the 7 coordinated intermediate or activated complex, and therefore it is not the RDS, rate determining step. It is an equilibrium reaction. So let us discuss the second step in this reaction, that is SN1 conjugate conjugate base mechanism. Okay, in the second step, that is the first step is very simple, that is cobalt third ammonium complex. So X is your X you consider the Cl minus, okay, chloride ion is there. So cobalt third a reaction with OH minus, so it is your base hydrolysis reaction, it is not acid hydrolysis reaction. So base will abstract one of the proton from this ammonia ligand, and there is a formation of conjugate base, and there is a formation of conjugate base, okay, with elimination of one water molecule, and the overall charge on the complex is decreases by 1 unit. In the second step, if you consider the second step, okay, the second step is that CO NH3 4 times NH2, okay, X, and it having the plus 1 charge, it having the plus 1 charge. So this is your species. This species it undergo dissociative type of reaction, or it will dissociate this X ligand minus X ligand, X minus ligand, and what you get here finally, we get this CO NH3 4 times NH2, CO NH3 4 times NH2, and again due to the dissociation of this X minus ligand, the oxidation state, or the charge on this complex is it is increases by 1 unit. So again it is converted into plus 2 oxidation state. So the first step it is the formation of conjugate base. In the second step, if you consider, that is whatever the complex which is formed, okay, after uh, abstraction of proton, that is conjugate base which is formed, it undergo dissociation of this X minus, dissociation of X ligand, and there is a formation of intermediate. Okay, so this is your intermediate with coordination number 5, with coordination number 5. So this complex, that is in this case the coordination number is 6, so it undergo dissociation, of this Cl minus, or we can consider X minus ligand, and the intermediate is formed with coordination number is 5. So what this reaction indicate, that there is a dissociation of Cl minus or X minus ligand, and we get the intermediate with lower coordination number, and this is only happen in SN1 type of mechanism. This is only happen in SN1 type of mechanism, that is dissociative type of mechanism. dissociative type of mechanism, and this step, that is dissociation of this halides from this cobalt or conjugate base, it is your RDS, it is your slow step, it is your RDS redetermining step, it is your slow steps. So why this is your slow step? Because if you consider, or why the dissociation of these halogens is occur from the second step, the reason behind that, because of the deprotonated form of the complex has lower charge. So if you consider, this is your protonated form, this is your deprotonated forms, means proton is removed, and if you consider the protonated forms having +2 charge and the deprotonated form having +1 charge, and we already studied that as the oxidation, as the positive charge on the complex is increases, then the rate of ligand substitution reaction is decreases. So in this case, the rate of dissociation is very less as compared to this, because in this case, the complex, that is conjugate base complex which is formed, it having a lower charge as compared to the protonated forms. Okay, so it is your deprotonated, this is your protonated. D means what? The one proton is removed from this ammonia ligand. Okay, so deprotonated form. So the first reason is that the deprotonated form of the complex have lower charge, they having lower charge. So this complex having +2, this complex having +1, so they are having lower charge, and therefore the rate of ligand dissociation is very much higher in this second reaction as compared to the first reaction, because the first reaction is equilibrium reaction. Okay, so base will abstract one of the proton and there is formation of conjugate base. In the second step, why this complex, that is conjugate base complex, undergo dissociation of one of the dissociation of halogen ligands? Because the charge on this complex is low as compared to the protonated form, and it will be able to lose the X minus ligand more readily than the protonated form, and this is the reason. So we already discussed that lower the oxidation, lower the charge on this complex, it increases the rate of ligand dissociation, it increases the rate of ligand dissociation, and therefore this complex readily undergo dissociation of this X minus ligand or Cl minus ligand. Okay, uh, in addition, another reason is that, in addition, according to the conjugate base mechanism, the loss of proton from the ammonia ligand changes it from pure sigma donor ligand to a strong sigma donor and pi donor. Okay, so when, if you consider without, when you consider the deprotonated form, then this ammonia, it is your pure sigma donor ligand, but due to the abstraction of one proton, this ammonia ligand is converted into pure sigma donor ligand to strong sigma donor and pi donor ligand, and it will stabilize. Okay, so whatever this conjugate base which is formed by abstraction of proton, that is the pure sigma donor, it is converted into strong sigma donor and pi donor as a NH2 minus. Okay, so this NH3, one of the NH3, it is converted into NH2 minus. Okay, and therefore it is a strong sigma donor and pi donor. Okay, and it stabilize whatever the intermediate which is formed, so it stabilize. So there is a two reason. One reason is that the conjugate base have lower charge, okay, the conjugate base have lower charge, and therefore the rate of ligand dissociation is very much higher. And the second, that is according to the conjugate acid base mechanism, that whenever there is a protonation, and then the ammonia ligand, it is converted into NH2 minus, that is it will convert into its conjugate base, and the properties also changes. So it is converted into uh, sigma donor, pure sigma donor, to a strong sigma donor and pi donor ligand. Okay, pure sigma donor to strong sigma donor and pi donor ligands, and it will stabilize. Okay, so conjugate base. Okay, or we can consider this NH2 minus, that is your conjugate base. NH2 minus will stabilize the intermediate. It will stabilize the intermediate. Okay, so these are the two reasons why there is a dissociation of this chloride or X minus ligand from this conjugate base, which is formed after uh, protonation. After base will abstract the proton from one of the ammonia ligand, so the overall charge on the complex is lower as compared to the protonated form. And the second, whatever the conjugate base is formed, it is a strong sigma donor as well as pi donor, and therefore it will stabilize whatever the intermediate which is formed with coordination number 5. And this reaction, it is your slow step and it is your RDS. And what it indicate, the rate of this reaction is totally depend on the concentration of conjugate base, and therefore it is your first order reaction. Okay, and it undergo dissociative type of mechanism. Okay, so this is the second step. And in the third step, if you consider, okay, in the third step, that is this complex CO NH3 4 times NH2, okay, it having +2 charge, it will react with water. It will react with water. It will react with water, and there is a formation of this complex. That is, we get this, that is cobalt NH3 5 OH. Okay, and the complex again it is having +2 charges. Okay, so this is the reaction. So these are the three steps. Okay, and this reaction, it is your fast step. This reaction, the reaction with water is fast step. This is your slow step, and this is your rate determining step. And therefore this conjugate base mechanism follow the first order kinetics. Conjugate base mechanism follow the first order kinetics. First order kinetics. Conjugate base follows conjugate base mechanism follow the first order kinetics. Okay, so this is also the evidence for the substitution reaction, that is substitution reaction in octahedral complexes. Okay, and it undergo dissociative type of mechanism, no doubt. So you should remember these three reaction. Before these three reaction, you should remember what is hydrolysis and what is acid hydrolysis and what is base hydrolysis. In acid hydrolysis, equation reaction, it is also called as acid hydrolysis. Base hydrolysis means what? Whenever the base such as hydroxyl ion interact with your complex, then it is considered as base hydrolysis. So this conjugate base mechanism, why this mechanism is considered as conjugate base mechanism? Because after protonation, the conjugate base is formed, and therefore this mechanism is considered as a conjugate base mechanism. Again, it is considered as a SN1 mechanism, SN1 conjugate base mechanism, because this reaction follows first order kinetics, because the dissociation of this chloride ligand or the X minus ligand is a rate determining step, and therefore it is considered as a SN1. So it undergo dissociative type of mechanism. And this is also the evidence for the substitution reaction in octahedral complex by dissociative type of mechanism, that is through SN1, and in this case the conjugate base is formed. So at least you should remember this three reaction. That is, the first reaction is equilibrium step. Base, it will abstract one of the proton from this ammonia ligand, and there is a formation of conjugate base. After that, the conjugate base undergo dissociation of X minus ligand, that is your RDS, rate determining step, with elimination of chloride ions, and the charge on the complex is increased by 1 unit. And in the third step, that is your fast step, that whatever the intermediate which is formed, it will react with water, and there is a formation of the product, that is CONH35. So this ammonia, okay, conjugate base, it will abstract one of the proton from this water molecule, and then OH minus, it will interact with this intermediate and formation of this complex, that is CONH35, which and the overall charge on this complex is plus 2. So this is your first step. So this is also one of the important evidence. Many times the question is asked on this reaction for your CSR NEET and CET exam. Okay. So whatever the evidence is which is left, we will discuss in the next lecture. Thank you.